Okay, good morning. Let's start. So we are now entering the second third of the course, which means that we already finished the first third of the course, namely our investigations and explorations in probability theory. Last week with these collections of results from expectation, covariance, inequalities, and limits. And as I mentioned at the beginning of the course, the whole first third was supposed to be like a precursor and establishing some preliminary stuff that we will need further on. And now we are at this place where we are further on, and we will start with frequentist inference, or as you also can call it, classical statistics, or classical frequentist statistics, whatever suits you. And that's the second third. So today we are then really entering statistics proper and building upon the stuff that we discussed in probability theory. So frequentist inference is now the second big chunk of the course. And today I first want to talk a little bit about foundations of statistical inference in general, and then talk about some basic aspects of classical frequentist statistics, before then going into an important method to come up with parameter estimators in parametric statistical models, namely maximum likelihood. And you might have noticed that in standard machine learning courses, maximum likelihood also is featured heavily. That doesn't mean that maximum likelihood is something very specific to machine learning or something. It's definitely statistics. Was maximum likelihood. This idea was really put into practice and formulated explicitly by Fisher in the 20s. And of course it was used before. And now, of course, it's very important in statistics, but as you also know, it's also something that people call machine learning these days, or some people might even call this artificial intelligence. Anyway, it just shows that it's everything, or that all is the same. So the material rests on mainly Wasserman for kind of this general introduction, and then when we talk about a specific numerical approach for maximum likelihood later, that's basically from the Held book. So that's the outline. First, some foundations on statistics and statistical inference in the frequentist setting in general, and then maximum likelihood with its own foundations, an analytical part and a numerical part. Then let's get going, if there are no questions right now. No. Good. So first, talking about some very foundational aspects of statistics. The question, what is a statistical model? And one definition that works and is general enough so that one can actually apply it in many cases is that a statistical model is a set of probability distributions. And a statistical model I will often denote here by this calligraphic P. And if one uses this definition of a statistical model, then one can already distinguish two very important forms of statistical models, namely parametric statistical models, where we can parameterize the statistical model by a finite number of parameters, and a non-parametric statistical model as being a model that that cannot be parameterized by a finite number of parameters, so where you basically need infinitely many parameters. As you will have noticed, most of the stuff that we are doing here is parametric statistics. We will have this one session on non-parametric statistics where we discuss some aspects of that. In general, I'm more kind of a parametric statistics guy, based on my personal experience that if you want to do non-parametrics really good, you need to put in some assumptions, which you best do with some parametric probability distributions, and then you're back to parametrics. So non-parametrics, from my perspective, only goes a certain way. Yeah. So we are then now focusing in, when we talk about frequentist statistics, for most of the part on parametric statistical models. Also in Bayesian inference, we will talk about parametric statistical models. Again, there will be a session on non-parametrics, but for the most part, it will be parametric statistical models. And in this case, the statistical models that we're dealing with have such a form. So usually these parametric statistical models are specified in some form of probability mass or probability density function, which is parameterized by theta, which I denote here with this subscript. There is a parameter, small theta. This parameter can often be a vector, can be a scalar. Read it, I would suggest that you read it in general as a vector, and if then things don't work out, and I haven't said I mean a scalar, then it must have been a scalar. Later on I will sometimes remark that theta is a scalar in this case, but in general, of course, a parametric statistical model can have more than one parameter. So in general, theta can be a parameter vector, and this big theta is a parameter space. So we will use this notation throughout. These are then typical, or very basic, but also very typical examples of parametric statistical models and how we will talk about them. So we will very often assume that we have n random variables which are independent and identically distributed. These random variables x1 to xn model data points. Yeah? So we are, of course, if we write something like this, we have this intuition that we have observed n data points for which we assume that they are realizations of n independent and identically distributed random variables. This idea of this kind of a random sample we write as this, so that these x1 to xn are distributed according to probability mass function or probability density function p underscore, in this case, mu. And the important thing is that this p mu, the probability mass function in this case, is then an element in this set of probability mass functions, which makes up this metric statistical model. So in this case, it's all the Bernoulli probability mass functions. So the idea is this random sample is distributed according to the Bernoulli distribution, and mu is some value in 0, 1. So the parametric statistical model itself is the collection of all these different probability mass functions. Here's another example. So here we have these independent random variables, the modeling data points, distributed according to, in this case, a probability density function, namely a normal or Gaussian probability density function, a univariate one. And in this case, the parameters are, or the parameter vectors, so the theta is mu and sigma square. So we are considering all the probability density functions. We can debate this definition a little bit, so especially with regard to the number of random variables. So for example, if you think about power calculations, I think it makes sense to consider also the number of random variables, so the random variables as part of the parametric statistical model. It depends a little bit. It's with these general, very general definitions are of course only useful to a certain degree. Here's another example for a parametric statistical model with which I hope you have some experience, namely the general linear model, where actually the random variable is d-dimensional. You can have a design matrix and some parameters, and you have normally distributed and independently distributed error terms, which corresponds to a probability density function over these d-dimensional data points. And yeah, then you can think about sampling n of d-dimensional data points, and you would write this like this. I assume that most of you have discussed simple and multiple linear regression, t-test, ANOVA, and ANCOVA in your undergrad statistics, and these kind of methods, they are all special cases of the general linear model. So here, who has done a course on general linear models? Who is aware that multiple linear regression and ANOVA are special cases of general linear models? That's the new imaging people. That's not that awesome, because general linear models are kind of, in classical frequentist statistics, they are really the workhorse that unites all of these things. So ideally there would be a course on general linear models, maybe even generalized linear models in your program. I'm just mentioning this now. We will at one point see an example of simple linear regression and so on. But if you want a course on general linear models, join the SCAN program where I'm teaching general linear models every year. So if you want to learn more about general linear models, that's one way to go. Or read this new book by Seba, which is also good. Now, so that's examples for statistical parametric models. And now we're zooming in a little bit more, namely we're talking about frequentist inference first. And in frequentist inference, there are three kind of standard problems that we will discuss. And they are introduced on this slide. So one important problem in frequentist inference, but of course also in Bayesian inference, is parameter estimation. And the aim here is to find a best guess for the true but unknown parameter value of the model, typically based on the observation of n independent and identically sampled random variables from this model. So parameter estimation is a problem. Another typical problem of frequentist inference is confidence interval evaluation. So the aim here is to provide a quantitative uncertainty statement about the parameter estimate based on the parameter estimator's sampling distribution. So we're thinking about sampling from the model, and then based on the distribution of the parameter estimators, we want to have some kind of interval estimate of the parameter with a specific interpretation that we will call confidence intervals. And finally, something that is very prominent in classical frequentist inference is also hypothesis testing, which you have, I guess, all encountered with where you do a t-test. And here the aim is to decide based on some observations whether the true but unknown parameter is in one of two mutually exclusive subsets of parameter space. Of course, we will discuss each of these problems in some depth, starting with parameter estimation. Once we're done with parameter estimation, we will discuss confidence intervals and then hypothesis testing. One more general term that we will use throughout is the term of statistics, or statistics in general. Statistics, or a statistic, is just a function of the observed or observable random variables of the random sample. Yeah? So if somebody asks you what is a statistic, then you can say it's a function mapping random variables that or a random sample to some value. And because it's a function of values of random variables, it's itself random. Yeah. So this slide, of course, it doesn't make clear all of these things, but it just states that the big problems are parameter estimation, confidence interval evaluation, and hypothesis testing. Here's a visualization for this basic idea of how statistics in general works. It's a little bit similar to what I've shown you earlier in terms of this model-based approach. What you always need to keep in mind about the whole statistics approach is that there's the assumption that in the world, there's one true but unknown parameter value that governs the distribution of your random sample x1 to xn, and that's fixed, and that's in the world, and you will never know what it is, but you can observe x1 to xn, and based on your observations you can try to make statements about that. But this true but unknown parameter value will never be revealed. What you can do, and what we will discuss, is you can come up with point estimates for that. So this dash thing here is supposed to show this true but unknown parameter value, which you will never know. But you can provide a best guess for it in terms of a point estimate. The reason why I include that here, although you will never really know it, is that in theory, and when you try to evaluate how good estimators are, you cannot, of course, assume that the true but unknown value takes a specific value, and then you can ask how good is my estimator with regards to the true but unknown value that I assume. But the real true but unknown value that governs the distribution of your data, you will never know, and it will always remain unknown. Hence, true but unknown, always unknown, never recovered, never known. So in frequentist inference, just coming back to the slide before, you can do point estimation. So you try to come up with a best guess for it, and you can think, if I have different values of the true but unknown parameter value, how good is my estimator doing? You can do a confidence interval estimation, where you try to create random intervals that include your parameter with a certain probability, which we will also discuss. And you can do, in terms of inference, hypothesis testing estimates, where you basically just ask, is the true but unknown parameter in one part of the parameter space or another part of the parameter space. So the way I view this whole thing is that your kind of uncertainty, you allow for larger parts of parameter space in terms of uncertainty. If you do a point estimate, you say, my best guess here is 2.1 for this true but unknown parameter. If you do confidence intervals, you say, okay, my best guess is that, and we will discuss the interpretation of confidence intervals, but roughly you say, with 95% probability, the true parameter is captured by this confidence interval, and you say it's in a certain range. And in hypothesis testing, you just say, the true but unknown parameter is either, for example, smaller 0 or larger 0, or you say it's 0 or something else. So these forms of frequentist inference are go at different granularity about your statements about the parameter. And we will discuss all of this in detail. Good. Any questions about these foundational aspects? Something that you've heard before that is in conflict with what I've just said, something that you don't understand from my general remarks here? Everything clear. Good. So based on this very little foundational theory of what a parametric statistical model is, and what the basic problems are, we now consider a point estimation, of course, as the first big problem. And for point estimation, we discuss maximum likelihood estimation as a general principle of deriving estimators. There are other ways to come up with estimators. One example that we will see briefly in the Übung is the method of moments, which is also a general principle to come up with estimators. So maximum likelihood is by no means the only method to come up with estimators. Of course, you also know that there's something like Bayesian inference, and if you, for example, look at the expected value of the posterior distribution or the mode of the posterior distribution, then you also come up with point estimates of the true but unknown parameter based on a different principle, which is then not maximum likelihood estimation, but basically Bayesian inference in the sense of evaluating posterior distributions. Sometimes they then come up with similar results, so that some form of posterior distribution feature inference is the same as maximum likelihood estimation. So maximum likelihood estimation is not the only way you can come up with estimators. You can also come with estimators just by guessing, so just by proposing, let's estimate this parameter like this. All of this is possible, and the important thing is then, of course, to study how good these estimators are, and this will be then the topic for next week and the week after, because like a principle to come up with estimators is nice, but the question is then how to evaluate these estimators and what are good or bad estimators. Good. Then also for maximum likelihood, first some foundations. Of course, we first need to use the term already, but we should be a little bit more specific. What we mean by these things. What is a point estimator? We will always make the same assumption now, and I will write it up quite often. I hope that it's not too different the way I write it up, but in general, for everything that we do in the following, we will always assume that there's a parametric statistical model, that there is a random sample, meaning that there are x1, xn, which are n independent identically distributed data points. Of course, these are random variables. They have over some outcome space, and the distribution of xi, where I is 1 to n, is defined in terms of the probability mass function or probability density function p theta of x. Yeah, so this will be a common assumption that is behind everything. It will often show up. If it doesn't show up at a certain point, then just assume that it was meant to be also there. Maybe something that I didn't stress that much. This PMF or this PDF, they describe the distribution of one of these data points, yeah? We assume that we have n of them, so keep that in mind. So these PMFs or PDFs are not distributions over the entire random sample in general. Of course, you can express the distribution of the entire random sample, but and we will see that, but it's meant to be that this is the P theta x is the PDF or PMF of the distribution of one of these random variables. Now, a point estimator then is a function of this random sample, and we write this as theta n with argument x1, xn. And again, as I already mentioned earlier, ideally I would love to write theta n as really as a function, so where you define the domain and the range. And then you start to wonder, so is the domain now, do I by the domain mean these random variables, so it's a function space, or do I mean by the domain the values that these random variables can take on? So for example, n-dimensional real vector space. And essentially, to avoid these discussions, and also because they don't really help to make progress, we don't write domain and range down here, but just appreciate that a point estimator is a function. It works on random variables, and then returns an estimate that is a single best guess of some quantity of interest. So maybe what one should include here is that it returns a single value. The important thing about estimators, and this is what you really need to appreciate, is that the point estimator itself is a random variable. Yeah, so the basic idea is, so think of the point estimator for most of the time as the sample mean, or let's say the maximum likelihood estimator of a Gaussian expectation parameter, which is the same as a sample mean. You put into the sample mean, you put into the realizations of random variables, which you average. But you always need to think that you could sample your parametric statistical models many times and always compute the sample mean, or always compute this maximum likelihood estimator for a Gaussian, and then you would always get different values. And if there's some variation in the data that is observed. And the important thing then is to appreciate that an estimator is itself a random variable, because it varies. It's random as a function of the data points, which are random because they are generated or assumed to be realizations of random variables. So this is really important. important difference between point estimator and point estimate. If the point estimator takes on a specific value, and it will always, of course, take on values in the parameter space, then this point estimator is referred to as a point estimate. So think that the true but unknown value is 2.3, and you evaluate a point estimator based on some random sample, and you evaluate this point estimator to be 2.7. Then this 2.7 is your point estimate of the true but unknown value. Yeah, so estimates and estimators are different things. And frequentist inference is in generally highly concerned with the properties of point estimators, which we will see in terms of the qualitative aspects in the next two sessions, and in when we talk about hypothesis testing and confidence intervals, of course, also the distributions of point estimators will feature heavily. And to come up with point estimators, so because a point estimator is also another point estimator is like if your parameter spaces, for example, are the real numbers, then a point estimator is also hat theta n equals 4. So this disregards the values of x1 to xn. It's a constant a function, but it's a function. You can view it as a function, and it's an estimator. So there are different ways to come up with point estimators, and maximum likelihood estimation is just the most common method for point estimation in parametric statistical models. Yeah? Maybe one more thing, the subscript n here is always to indicate that there are n random variables. We will need this later on because we think about what happens if we have more random variables, so more data points essentially, and then the estimator is also a function of n in the sense that it's based on more or less or more or fewer data points. Yeah? Point estimator. Questions about point estimators and point estimates right now? You can also call them statistics. It's not the most typical use of the term statistics, because in statistics you not necessarily map into the parameter space. Like, for example, the T statistic, for example, for GLN doesn't map into the parameter space, and that's more usually then called a statistics because it's a function of the data. But of course, a point estimator is also a function of the data or the random sample, and hence it's also a statistic. Good. Then, if it's clear what a point estimator is, the question is now how to derive a point estimator under the principle of maximum likelihood. And to do so, we need to first define what the likelihood function and the log likelihood functions actually are, because maximum likelihood just means you get a good estimator by maximizing the likelihood function or the log likelihood function. And I assume you've seen this before. So who has learned about maximum likelihood estimation? Okay, who has implemented maximum likelihood estimation? Okay. The likelihood function is interesting. It's a function of the parameter of a parametric statistical model, which is mapped onto positive real numbers. And the value that it takes on for a given parameter value is the joint density or joint probability mass of the data points. Yeah? And the joint density is given by the product of the densities of the individual data points. Why? So why do we have this product here? Yeah, exactly. Because the random sample, the individual random variables are assumed to be independent, hence the joint density is modeled by the product of the individual densities or masses, and hence we have the product here. So that's the independence and the identicality you see essentially here, because it's always the same probability density in which each xi is put in. Now Now, the important thing to appreciate about a likelihood function is that it's essentially a random function. So, or there are two things that are very important about likelihood function. First, as a function, the input of the likelihood function is the parameter. So the domain of the likelihood function is the parameter space. So it's conceived. It's a function of the parameter. Of course, it's defined as a probability density, but it's usually not a probability density, so it doesn't integrate to 1 over theta. So don't confuse that. It's a function of the parameter. The other thing to appreciate is that you should view these xi as a random realization of the data random variables x1 to xn. That means if you sample from your parametric statistical model again, your likelihood function will be slightly different, because you're now looking at the probability densities of different data points under this probability density, and you multiply this for different values. So, and then what you do is, when you look at the value of the likelihood function, you change the parameter value, because it's always a function of the parameter. But you can view the likelihood function. So the likelihood function is defined as this, but a specific likelihood function in a specific data analytical context is only one of many possible realizations of likelihood functions, because it's a realization that depends on the observed data, xi. So this is something to get used to. So I don't know what helps. So you can for sometimes think that the likelihood function depends both on the data and the parameter, but then you need to be careful when it's, for example, if you compute derivatives of the likelihood function, then it's always with respect to the parameter. And so it needs a little bit of time to get used to that. There's another thing called the log likelihood function, which is just the log of the likelihood function. This logarithmic transformation makes sense, or is very useful from a mathematical perspective. It turns this product into sums. It turns probability density functions from the exponential family into less complex functions. It basically avoids that you're dealing with very small values close to 0 all the time. So it has a lot of beneficial consequences, and it doesn't change the location of maximum likelihood estimates or estimators, because it's monotonic. Thank you. It's a monotone transform. So it if the input is if there are two inputs and one input is larger than the other, then also the output is larger, and it hence does not affect where maxima are located. So I think there are some of these remarks later on. So again, the value of the likelihood function is the joint density of the data, where the joint density is given by the product. It's a function of the parameter. It's not a... I don't know why people try to confuse that. So, but there's no reason that the likelihood function should integrate to 1 over theta, because these were probability density functions over data. So yeah, it's not a probability density. Good questions about the likelihood function? Good. Then, based on the likelihood and log likelihood function, we can define the maximum likelihood estimator, which we define as the argument in parameter space that maximizes the likelihood function, or equivalently maximizes the log likelihood function. And I think this will be the notation that I hopefully use then throughout for the maximum likelihood estimator. And there's a hat on it because it's an estimator. There's an n on it because the idea is that it's based on n observations, because again we will increase the number of observations or the number of data point. And there's an ml on it because it's a maximum likelihood estimator. This is what we briefly discussed, because the logarithm is monotonically increasing. The maximum of the log likelihood occurs at the same place as does the maximum of the likelihood function. We could delete this here. Essentially, working with the log likelihood function is just easier. This is a remark that's in the Wassermann, which is sometimes helpful when you're doing when you're doing maximum likelihood estimation. So if you have any constant contributions that do not depend on theta in the likelihood function, then you can disregard them, because as they are not a function of theta, they don't change where the maximum with respect to theta is. In general, when I do maximum likelihood estimation and derive or write down likelihood functions, I'm not the biggest fan of then, like in machine learning books, where it then just plus some constants, and then it gets a little bit messy. So I like to be explicit as long as it's possible. Anyway, of course, you can discard constants in the likelihood function, as you can discard constants in any function that you're trying to maximize or minimize. And then the important thing, of course, based on this definition, is that maximum likelihood estimation is a standard problem in function maximization. So basically finding the maximum of a function with respect to its input argument. And of course, you did this in school when you did calculus, essentially. So you try to find the extremal points of functions, so minima and maxima. And what you did to this regard was to compute derivatives, and then you learned that a necessary condition for a maximum or minimum, so for an extremum, is that the first derivative is 0, because basically the first derivative, of course, is the slope, and at maximum or minimum, it just changes its direction, so going from a negative slope to a positive slope, and then for example, for minimum. So you know how to maximize or minimize functions to a certain degree. And if you are then faced with the problem of coming up with a maximum likelihood estimator, you basically need to tap in your knowledge about function maximization. So this is then a general procedure for doing maximum likelihood. So the first thing, if you written down a parametric statistical model that you now want to use to model your data, and then start with estimating some parameters from it, the first thing that you need to do is to formulate the log likelihood function. And that's relatively straightforward, because you have defined the probability density or probability mass function of your data points. You usually would assume independent sampling. If not, you can still write it down, but you might have to think a little bit harder. And then you basically need to log transform your probability mass functions and your probability density functions. So that's the first thing that you need to do, and actually you need to do that either whether you do that in a analytical or numerical fashion. And then in simple parametric statistical models, like in textbooks, you would then maximize this log likelihood function by the standard procedure that you are familiar with from school. So you compute the derivative, set to 0, and solve for the critical point. And then, of course, you would need to do what you learned in school to verify that it's a maximum. You have to check whether the second derivative is actually negative. Of course, this gets more complex if you have a function of multiple parameters. And often, actually, in statistics textbooks, this checking whether a critical point is actually a minimum, is actually a maximum, is just not done. One can address this from different angles. So one can also first establish that the log likelihood functions are concave or strictly concave, strictly convex, and then ensure that these then always have minima or maxima, depending on which whether you look at a positive or negative likelihood function, log likelihood function, use this. So don't be too let down if you always in kind of machine learning statistics books only see this, okay, we compute the derivative, we set to 0, and then we have a candidate for our extremal points, for our maximum likelihood estimator. And then it doesn't continue with checking also the second derivative. It's just how it is. However, this kind of thing, basically trying to find the 0 of the log likelihood function's derivative, this can of course also be done numerically. So the general procedure is here: you need to write down the log likelihood, you evaluate the derivative, set it to 0, solve for critical points, and then verify that it's a maximum. And this is of course strongly what you would do in an analytical setting in these classical examples. In real life, you would basically only have to really do the first step, and then use some form of maximization that is numerically done. And in so in the next hour we will then look briefly at some classical examples of this analytical function maximization, and then in the second part look at one way you can do a maximum likelihood estimation numerically based on a specific algorithm, namely Newton-Raphson and Fisher scoring. But of course, numerical likelihood estimation can be done with many different algorithms. Other questions about what we've seen so far? It's fairly general, but it's also good that it's that general, because then you can use this now for all your favorite parametric statistical models that you specify for your data. Yeah, good. Then let's have a break here and continue 10 past 11. Okay, then let's continue with maximum likelihood estimation. And the first half then of this hour, I would like to look at some or two classical maximum likelihood estimation examples that you always see in the books and that demonstrate this basic idea of how to derive maximum likelihood estimators based on the idea of maximum likelihood. And this would be the problem of estimating the parameter of a Bernoulli distribution and then estimating the parameters of Gaussians. I assume that most of you have seen this before, so I think it's fairly quickly established. One thing that I forgot to say, I think, earlier on, is in terms of the intuition. What is this supposed to mean? So why do maximum likelihood estimation at all? Of course, the idea behind this is that you find a parameter value such that the probability, now I'm not going into details about density or mass functions, so that the probability of your observed data becomes maximal in the other way. Or saying another way of saying this is that you choose a parameter value as your guess for the true but unknown parameter value, such that under your guess, your observed data has a high probability. Actually, it has the highest probability for all of the choices you could make for theta. Yeah? So hence, this is essentially the intuition behind that. So that from all the parameters that you could choose, you choose the one under which your observed data, the data that you actually have, has the highest probability. Good. Now armed with this intuition, going into the analytical way of doing maximum likelihood estimation. As I previously mentioned, this is essentially an exercise in function maximization. the thing with these textbook examples, how to do it for Bernoulli random variable, how to do it for a Gaussian random variable, that's interesting to get used to this idea of maximum likelihood estimation in real life. Depending on the parametric statistical models that you set up, you would often actually use numerical ways. So these analytical examples in statistic textbooks, they are more of didactic purpose and that you really understand what's going on. But then, for example, once you have derived the Gaussian maximum likelihood estimators, then you can just use them, and you don't, when you use the maximum likelihood estimators for a Gaussian parameter, you don't always have to go back and show that these are the maximum likelihood estimators. Yeah, so it's more kind of an academic exercise. Although I wouldn't actually call this academic exercise. Academic exercise would be if I say, and now give me a lot of money, because it's academia. So it's more kind of a scientific exercise, maybe. Anyway, first example, we assume that we have n data random variables, each of them which are distributed according to a Bernoulli distribution. They are IID, and this Bernoulli distribution has a true but unknown parameter mu, and of course we want to estimate mu. So in terms of observations that you can make, of course these are n observations of zeros and 1, and of course intuitively you know if one of these observations of one of these random variable has a high probability for coming up 1, that meaning the mu is quite large, so let's say 0.9, then of course it's more likely that you observe data samples that have a lot of ones, and then it's if your mu is fairly close to 0, then it's of course more likely to observe data samples with more zeros. And maybe you even know already that the best estimate for the maximum likelihood estimate for mu is actually the sample average in this case. If you don't know that, this is how one can show that it is. So the first thing you always need to do, and when thinking about maximum likelihood estimation, is to formulate the log likelihood function. And I generally recommend to start with the likelihood function, because there you basically just need to write up most of the time then the product of the individual probability mass or density functions. In this case, it's the Bernoulli probability mass function, which is mu to the power of x, 1 minus mu to the power of 1 minus x. Now we have n of these data points, and so we need to index the data point here, write it as a product, and then one can, based on the fact that we have this under a product, we can basically put certain things here into the exponent. So we put the sum of the xi into the exponent, and here we put n minus the sum of the xi into the exponent. So always keep in mind that the xi in this case only take on the values 0 and 1, because we have a Bernoulli distribution. Yeah? Then you can take the logarithm, so we are dealing with this, and taking the logarithm then has these nice features that you basically get things in front. So if you have something here in the exponent, this will be a constant that you can write in front, and then you have a logarithm of the thing under the exponent. It's written the other way around here for I don't know what reason. So taking the logarithm then usually simplifies things, and that's what's shown here. And then you already have the log likelihood function, and you could now, one thing that I always recommend if you're doing maximum likelihood estimation is to also visualize the likelihood function, or better, the log likelihood function. For a given sample. So for example, you assume that you have like n data points, and let's say 4 of them are ones. then you can of course plot the value of the likelihood function as a function of mu and look at it and see where the maximum is. As you know, my lecture slides this year are very short on visualizations because I focus on the content. Next year there will be visualizations, so I don't have a picture, but in general, when you do maximum likelihood estimation, always visualize the likelihood function and the log likelihood function, so then you get a feeling of whether this has a well-defined, or not a well-defined, but that it has a nice unique maximum or not. So do that. Then to do this standard function maximization business, you of course would compute the derivative with respect to the parameter and set to 0. So this is then in these textbook examples, this is a little exercise in doing derivatives, and here the derivatives are done. So yeah, I don't think there's anything of great value in this. I mean, the most important thing is that the derivative here of the logarithm is 1. So the derivative of ln x is 1 over ln x, as I guess you all know. And then then you have the derivative, and then you would set the derivative to 0. And setting the derivative of the likelihood function to 0 is then usually called a maximum likelihood equation. So for example, in general linear models, these equations are called also normal equations. These are equations that say that a maximum likelihood estimator satisfies this equation. And then sometimes you can solve these equations for your estimator, as in these little examples. Sometimes you just need to find a way to find some value for your estimator that fulfills this equation, and you're focusing more on estimators that fulfill this equation. In any case, you after formulating the log likelihood function and computing its derivative, you formulate the maximum likelihood equation. And then I always, in principle, it makes sense to not use just the mu anymore, but to designate that we here have at least a candidate for a maximum likelihood estimate. Hence, I put a hat on this already. You could also put on the hat MLN already. I didn't do this originally, and then I didn't do it yesterday. So on the other hand, we haven't really shown that, well, you could also put the ML in here. And then you would solve for that, and yeah, in this case, this needs a little bit of small steps. So work over it, point out if I put in any typos in here. The important thing is what you come up with in the end is another equality, namely n mu hat is the sum of xi, and then resulting in that a maximum likelihood estimator here is 1 over n times the sum of the xi. Again, the xi are just ones and zeros, so if you have 3 ones in a sequence of 5 data points, then you have 3 over 5. So you can also interpret as kind of the observed frequency of ones is your maximum likelihood estimate. After solving for critical points, of course, you only establish that this is a candidate, but you haven't established that there's actually a maximum at this location. And to make things simple, I put in this can be consolidated, and then we have the maximum likelihood estimator for the parameter of a Bernoulli distribution, which is given by, you can call it the sample mean, or you can call it the number of ones divided by the total number of samples. In any case, it's 1 over n times the sum of the xi. Yeah, so that's basically deriving the maximum likelihood estimator for a Bernoulli parameter. Questions? No? Good. The second example, very conventional example, of course, to estimate the parameters of a univariate Gaussian based on IID samples. And in this case, we assume that we have n random variables / n data points that are distributed according to a normal distribution, univariate normal distribution, each of these with expectation parameter mu and variance parameter sigma square. And again, if you want to do maximum likelihood estimation, you follow always the same procedure. It's like a cookbook recipe. So the first thing is that you would formulate the log likelihood function, meaning again that you ideally start with the likelihood function, which of course in this case is the product of the univariate Gaussians that govern the distribution of each of this xi, and then you have the product, and you can so have the product of exponentials, which you then can transform into the exponential of the sum over these terms, which is helpful. And you can again put things into the exponent, and then you take the logarithm, and then you get these typical expressions that you see in all the books when it's talking about the Gaussian, where you have this ln 2 pi ln sigma square multiplied by something, and you this then of course also a nice feature of the logarithm when dealing with distributions from the exponential family. This exponential goes away and you end up here with a sum. And then you have the log likelihood function. And again, you would start to maximize that. And when maximizing, again, you would compute the derivative. In this case, I denote it with the standard derivative. You could also argue that, of course, we have a function here of two input arguments, so you actually compute partial derivatives. But of course, you know that if you compute the partial derivative with respect to one with respect to one input argument, that is, you keep all the other input arguments constant. Could have used partial derivatives here. Would have been a little bit more correct. You can just do that. Of course, you see that certain terms here in the sum only don't depend on parameters at all. So this doesn't depend on parameters at all. This depends on the variance parameter. This depends on both the variance parameter and the expectation parameter. So when computing the partial derivative with respect to mu, you end up with this. And when computing the partial derivative with respect to the variance parameter, this of course then should be the variance here. That's a typo. For me, it's the first typo today that I see, which is something. So what you can see here is what I did is I considered the likelihood function, log likelihood function, as a function of only one parameter here, and then this is why I don't compute partial derivatives. So then you end up with something a little bit more complex, but not really. In this case, you get two equations as maximum likelihood equations, namely this one and this one. And a little bit of a problem when applying this to the Gaussian, which has actually consequences all the time, is that the maximum likelihood equations for the variance parameter also depend on the expectation parameter. So there's some coupling in these equations, and this coupling is then, in the way of deriving this, is then usually solved by first solving this equation, and then based on the solution of this equation to plug the solution into this thing. So this is what happens here. So first solving for a critical point, the first maximum likelihood equation yields again the sample mean. So now our xi are not zeros and ones anymore, but they are real numbers that are distributed and have a certain mean. And if you take their sample mean, you have the maximum likelihood estimator for the expectation parameter. Now, if you substitute this into the maximum likelihood equation for the variance parameter, then you can rearrange this and end up with this maximum likelihood estimator for the variance parameter. For those who are very familiar with the sample standard deviation and sample variance, you might notice that there's no n-1 here, and that's actually a big story, and we will come back to that all the time. So the maximum likelihood estimator of the variance parameter is not the sample variance. And you also see that it's dependent on the maximum likelihood estimator for the expectation parameter. This also has consequences, and actually there's a whole other framework called restricted maximum likelihood estimation that for deriving parameter estimates that has essentially been invented to do away with the bad consequences you get from having these dependencies and having this n only there. So if you're interested in restricted maximum likelihood estimation, specifically in general linear models, that's what we will cover at one point in the winter term in the SCAN lecture, which always happens from 8 to 10 on Mondays. But yeah, so to summarize, the maximum likelihood estimators for the expectation and the variance parameters of the Gaussian are the sample mean and something that looks quite close to the sample variance, but with the difference that you divide by n and not by n-1. Good. So these are typical examples. Of course, one can do many more. One can look at this in more general models, for example, in the general linear model. So if you're interested in the maximum likelihood estimators for the general linear model, look into my PMFN on my website, into this probabilistic model for functional neuroimaging. There you find the derivations for the parameters of general linear models, which of course gets more complex because the parameters then are not single numbers where you can do partial derivatives, but you have parameters that are themselves vectors, so you have to compute derivatives with respect to vectors, and you first need to think about what that means and so on. So depending on your parameters, of course, doing this can be a little bit more complex. But for example, for general linear models, it's also all analytically established, and you can have your maximum likelihood estimators as formulas. Yeah, so that's the other thing that you should take from this analytical maximum likelihood estimation. You end up with formulas how to compute the maximum likelihood estimates, and these formulas are most often quite intuitive because there are things like the sample mean. But then the sample mean is not just the sample mean, but it's actually fulfills a sensible criterion as an estimator, in the sense that it's a maximum likelihood estimator, which is something. Yeah, good. Any questions about these analytical things? So do a couple of examples of this, and then once you're used to it, and you've done a little bit of computing derivatives again and solving little algebraic equations, then I think you have a good understanding of how you come up with analytical maximum likelihood estimators. In real life, most of the time, you will actually use something that is of numerical nature. So you will have a parametric statistical model. And then because you define the parametric statistical model, it's not something that falls out of nowhere. It comes essentially out of your head. You write it down. You have some reasons why you want this to model your data. Then it's fairly straightforward to write down the log likelihood function. But then you feel like, this log likelihood function, and now computing derivatives with respect to the parameters, and well, there's this, I have all of these canned codes and so on, so why not do this numerically? Let's not even start trying this analytically. And so you will write down the log likelihood function, otherwise you cannot do maximum likelihood estimation at all. But then you will use some numerical way of finding a maximum. And so numerical maximum likelihood estimation rests on first formulating and implementing the log likelihood function. So you need to write down, you need to program a function that returns for a given observation and for a given parameter value the log likelihood of the parameter that you then can subject to some kind of function optimization, as you're familiar from programming. The reason why I put this here, equivalent to negative log likelihood minimization, is that most of nonlinear optimization, numerical nonlinear optimization, is framed in terms of minimization. And with maximum likelihood estimation, you obviously want to maximize something, because you want to maximize the probability of your observed data for different parameter values. However, when you then start to look into numerical approaches, everything is about minimization. And of course, minimizing or maximizing a function is the same as minimizing the negative of that function. So to do numerical maximum likelihood estimation, you usually will have to put a minus sign in front of your log likelihood function in order to use this minimizing routines from numerical optimization. It's a little bit annoying, but that's how it is. The problem is then, of course, one problem in nonlinear numerical optimization, which can be done by many things. So you have things called deterministic or stochastic optimization. You can do constrained versus unconstrained optimization. If you have, for example, parameter spaces that, for example, like in the Bernoulli case, vary between 0 and 1, why not use some constrained optimization? Local optimization versus global optimization. Of course, the question is always, do I get stuck in a local minimum or maximum? Can I also identify the global one? And then you can look whether you want to use global or local approaches. And then, of course, you all know from neural networks that you can do gradient-based optimization. But of course, there are also means, for example, if you're familiar with MATLAB, there are these Nelder-Mead things that are gradient-free, where you don't need to compute derivatives and so on. So there are millions, let's say hundreds of algorithms, thousands of algorithms, which you can use to numerically maximize or minimize a function. You can also just evaluate the function for a discrete set of parameter values and just look where you get the minimum, and then take this as your minimum or maximization. So there is no boundary to your imagination in terms of numerical maximum likelihood estimation. So far, my favorite book on general optimization is this Not So Dull and White book. So if you're into optimization, read this book. And we, in the last 20 minutes, will only consider one method out of this thousands of methods that you can use for numerical optimization, just because why not? And it's also one of the reasons why looking at this is because this Fisher scoring algorithm, you find that in the statistical literature. So I think kind of in the late 70s, people developed a lot of different methods to estimate general linear models and specifically mixed linear models, where you have random and fixed effects, and they used kind of a set of methods that are related to expectation maximization and Fisher scoring. And these things, they were then implemented in these general purpose statistical software toolboxes like SPSS and I don't know, Stata or something, but SPSS, for example. And yeah, and their Fisher scoring plays a role. So that's why we look at that. Any general question about numerical maximum likelihood estimation? No. Good. So Fisher scoring is a specific form of the Newton-Raphson method for numerical identification of function extrema. And to hence introduce Fisher scoring, we first talk about the Newton-Raphson method. Who knows about Newton-Raphson? We've seen that. Who knows gradient descent? Yeah, do you know it because you called a function that does gradient descent, or did you study gradient descent? So who studied the theory of gradient descent and convergence of gradient descent and so on? Okay, yeah, that's kind of toolbox culture. I detect it in data science more and more. I don't like that. Anyway, so I have a strong issue with toolbox culture in neuroimaging, and I see it's happening in my new field. Wherever I go, the toolboxes seem to follow. Anyway, good. Yeah, Newton-Raphson is somewhat related. It's a little bit more complex than gradient descent. So in gradient descent, you basically just go into the direction of steepest descent, which you can get from the gradient. And the question is then, how far do you go? And that's the big problem. And Newton-Raphson does a little bit more, but also not much more. So let's have a look. What is Newton-Raphson? Newton-Raphson is an iterative approach to find extrema of univariate real-valued functions, which look like that. So we are basically going out of maximum likelihood estimation for a moment and just talk about any kind of univariate real-valued functions. And it's based on the idea that at the location of a maximum or minimum, the derivative of this function is 0, because that's the necessary condition. And of course, it's an iterative procedure. You start from an initial guess, and then you compute iterants, so updates of your parameter estimate. And what's happening actually here in Newton-Raphson is that you iteratively approximate this maximum point by using a first-order Taylor approximation of the derivative. So that's kind of the crucial thing. You can also view that as that you're looking actually at a second-order Taylor approximation of the original function. And we will see what that means in a second. And then, of course, for maximum likelihood estimation, the function that we're interested in is a log likelihood function. Yeah? So again, when you study this, think that first we are establishing this now for any kind of functions, and then we're looking into the specific form of functions, namely log likelihood functions. So the basic idea is that you want to evaluate a 0 of the derivative, because if the derivative is 0 at a point theta, then there is an extremal value of f at this location. And to do so, because this function might be complicated, you use a first order Taylor approximation of the derivative, where am I happy with this? I think I am. Around this expansion point, which is one of your iterants. Yeah, so you basically do the typical first order Taylor. So you take the function at a specific value and then look at the first derivative. The only thing that makes this whole Newton-Raphson a little bit complex is that it always looks a little bit different than you're used to, because in a first order Taylor, you of course here have the value f at the expansion point, and because we're looking at the first derivative, you have the derivative here, and it's a little bit confusing here. You also have the second derivative, because that's the first derivative of the first derivative. So that's the only thing that makes this a little bit hard to look at, but then it's relatively straightforward. If you assume you will take a first order Taylor approximation of this function here, this function here, and the derivative, the approximation is this, then by identifying a 0 of this Taylor approximation, you can essentially get a rule or get a value for the update of your parameter, because you can solve this for the 0, and then you find that it's this theta k minus the derivative at theta k divided by the second derivative. So to show this with a picture, So here you have the derivative of a function f, and you want to find its 0 point. Yeah? And to do so, you start somewhere, let's say at theta k. You consider the first order Taylor approximation of this, so the line essentially here. And then you identify its 0, yeah, in this update sense. And you get to this by this update rule here. And then you do the same thing again. So you approximate the function in this new value of the parameter by a first order Taylor, and then identify again its 0 here. And then by doing this and identifying always the 0 of this first order Taylor approximation, you get closer and closer to the 0 of the derivative. And once you have found the 0 of the derivative, you have a critical point, because that's a necessary condition for an extremal value. Of course, then you need to check that it's a maximum. So in algorithm form, this basically works like any algorithm. So you find a starting point. If the starting point is already fulfilling the condition that the derivative is 0, then you already won, so you can stop. If it's not, then you update your parameter estimate according to this rule, which you motivate from finding the 0 of the first order Taylor approximation of the derivative. That's essentially the univariate Newton-Raphson algorithm. You can also view this, if you don't like this thing about doing a first order Taylor approximation to the derivative, and you want to know, so what is this really doing in terms of the function, because I'm interested in the function and not so much in the derivative, although you are actually interested in the derivative because the necessary condition for a maximum or minimum of a function is that the derivative is 0. In any case, if you're more interested in the function, you can also derive the same update rule by considering a second order Taylor approximation, again in the expansion point corresponding to one of your iterants. So of course you cannot always start here with k0. So you write down the second order Taylor approximation, and then you reformulate this again, look at the derivative, and then you end up with exactly the same update rule. So that's also interesting. It needs a little bit of nitty-gritty derivative here. One important thing, if you go over this, is that theta k, that this theta k is a constant. So you have many constant terms, and you need to compute the derivative with respect to theta. So you can view these as constants. This is the univariate case. Can be motivated again as a by means of minimal by finding the 0 of the first order Taylor approximation to the derivative, or the second order Taylor approximation, the 0 of the second order Taylor approximation of this function f. Of course, you're using Taylor approximations in this whole thing because the function f might be too complex, too complicated to do something. This was all if this parameter is scalar. Yeah, so if you have a univariate real-valued functions. Of course, often you have multiple parameters, and then you end up with multivariate real-valued functions because you have multivariate log-likelihood functions. And one can extend this univariate Newton-Raphson method fairly straightforwardly to the multivariate case by essentially just replacing the notion of a first order derivative and a second order derivative in this update rule by the corresponding things in multivariate real-valued functions. So what's the corresponding entity to the first order derivative in a multivariate real-valued function as opposed to a univariate real-valued function? So if you have a function of n inputs, so a function of a vector that maps onto a real number, so a scalar, and you are supposed to evaluate the derivative of this function with respect to its input, what do you actually evaluate? Exactly. And for the second derivative? Yeah, the Hessian. Yeah. The Jacobian is the first order for n to n, so multivariate two vector valued functions. So essentially, if you want to specify a multivariate Newton-Raphson method, you just substitute in. Of course, you could do this derivation again, but you can also just go about the intuition that you replace the first derivative by the gradient, because now your theta is actually p-dimensional. So you put in the gradient, which are the partial derivatives of this function, stacked one over another. You might also realize that the gradient is the transpose of the Jacobian for a specific function, when the output of the function is actually scalar. And you replace the second derivative, or the inverse of that, by the inverse of the Hessian matrix, which after years and years of always writing it up again, you will still sometimes write it up wrongly, but it's just all the second order partial derivatives. And so here you have the partial derivative with respect to first component of theta k p, and here you then do the second derivative with respect to theta 1, theta 2, and so on. And you put them all into one matrix, then you have the Hessian matrix. And because of Schwarz rule, actually the derivatives, whether you take them in this order or this order, are identical, so it's also symmetric. And then in case of maximum likelihood, you have a multivariate log likelihood function, and you can again then write down this Newton-Raphson algorithm, where instead of now having the first derivative, you have the gradient, and here you have the inverse of the Hessian, and you update your parameter vector. This already applies if you actually have just two parameters, right? So then of course here you have a 2 by 2 matrix that you invert, and here you have a 2 by 1 gradient vector, and this is a 2 by 1 vector. Yeah. So just introducing one more parameter actually gets you from just talking about derivatives and second order derivatives, gets you to gradients and Hessians. So that's multivariate Newton-Raphson, but it's not Fisher scoring yet. And now finally, Fisher scoring. In Fisher scoring, that's essentially Newton-Raphson. You can do it univariate and you can do it multivariate depending on your parameter space. But there are certain specifica in Fisher scoring that don't quite make it Newton-Raphson. So essentially Fisher scoring is a numerical approach for maximum likelihood estimation. And it's essentially the application of the Newton-Raphson method to log likelihood functions. So remember previously we just talked about maximization, minimization of functions. Could be any. Now we are considering log likelihood functions in particular. And one thing that is different here is that you often try to avoid the computational burden of evaluating the Hessian matrix, which is of course both dependent on your data realization and where you are in parameter space. So this can be computationally heavy to evaluate. In the late 70s. So yeah, it's a little bit hard to, I mean, it's sometimes people pretend that now with our new computers we can do everything, but then if you actually start looking, no, not really. So there are still computational burdens, and it's still there can be a heavy load in certain things. On the other hand, sometimes when something is motivated from computational burden, and that was computational burden a long time ago, then maybe that's actually not a computational burden anymore. So yeah, there would need somebody who has more experience in terms of the computational burden than me to say how this is, how one would see that now. In any case, the multivariate Fisher scoring algorithm applies to log likelihood functions. So we consider now again a parametric statistical model where we have a random sample that is IRD distributed according to some PDF. and we have a log likelihood function. And we consider the multivariate Newton-Raphson method as previously established, and instead of the objective function f, we consider now the log likelihood function. Nothing really changed, it's just a specific form of function. And now two things that will also come up many times in the remaining course, specifically in the frequentist setting. The gradient of the objective function we now, where the objective function is of course the log likelihood function, we now call the scoring vector. For today, this is just a name. So the gradient of the log likelihood function with respect, of course, to theta is called a scoring vector in statistics. It's just the gradient of the log likelihood function, and we write it as Sn, call it scoring vector, and then we already have this term of score in there. And something that will feature heavily in what is to come is the so-called Fisher information. And here we're dealing with a specific form of Fisher information, namely a Fisher information matrix, and we look at its expected value. So here we have the Hessian matrix of the log likelihood function. We can remember that I said that likelihood functions and log likelihood functions are random in the sense that for different data realizations they look different. If we compute their expectations over data, and we of course know the distribution of the data, then we can compute an expected value of likelihood functions and of log likelihood functions, hence also of the specific derivatives. And that means we don't, for each data point, compute something specifically, but just use the expected value that we might even then pre-compute as a function of theta. And for reasons that will become apparent, I think already in the next session, this derivative of the log likelihood function is called, the second derivative of the log likelihood function is called Fisher information with a minus sign in front of it. So again, the negative second derivative of the log likelihood function is called Fisher information. I will have more clean-cut definitions of the terms Fisher information, expected Fisher information, and so on next time. So this is just the first time that you see it, and the nice definitions will come next time. Here it's mainly there to replace the Hessian. And if you then plug these into your multivariate Raphson, then you get to what is called a Fisher scoring algorithm. Yeah. So if you now, when reading statistics papers, or as I call them, good machine learning papers, then you might come across the notion of Fisher scoring, and there you will always see the expected Fisher information matrix, which is the expectation of the Hessian. The sign changes, and you see what is called the score vector. And again, this is just the gradient of the log likelihood function. And then this is just Newton-Raphson method in a parametric statistical model for where you have log likelihood functions and where your objective is to maximize or to find an extremum of your log likelihood function. This paper I added to the course references. It's a nice overview about Fisher scoring. It's of course Fisher scoring. You see that if you Google that, you find some people being confused about Fisher scoring and so on. But Fisher scoring has been around for some time, but it's also not that old. Yeah? Fisher scoring is not something that actually Fisher made, I guess, because he did everything. Maybe he did it in one of his papers, but really Fisher scoring is kind of late 70s stuff. Yeah, stop if you have solved it and go to one more. Yeah, so that was then so that was one way of doing numerical maximum likelihood estimation, namely using Newton-Raphson and Fisher scoring. Of course, this is by no means the only way. One of the exercises in in the Übung is actually to do maximum likelihood estimation by maximizing the log likelihood of a specific model that's, I think, defined using your favorite function optimization routine, because there are just very many options. And then, of course, the question is, which should I use? And yeah, then look what people do and do what other people do. Good. Any questions regarding the numerical maximum likelihood approach? So, of course, just one tiny part of what can be used, but on the other hand, it's also covering basically everything, because it's then just a function, then it's just a question of function optimization. And that's then the big topic. That's the question.
The relationship between the quasi-Newton methods you have mentioned and the BFGS.
That's a very interesting thing. This is actually not a pure Newton method. This is the pure Newton methods then look a little bit different. And yes, there are these BFGS methods, which often then work by playing a little bit with the Hessian. Actually, I cannot really answer this right now. I mean, it's a big field, numerical optimization, and there are these
yes, but you still have to undergo a mini match to do the iteration, rather than the first order optimization with I can update the gradients after each sample. So that makes it quite seldom in use.
Seldom in use?
Seldom in use, yeah.
Yeah, I mean, but of course you also have people working on optimization, trying to find better methods, and whether they are being used then or not, it's also a different question. Yeah, but optimization is so if you really want to learn about data science, there are two things to learn about. One is probabilistic models, and the other thing is function optimization. These are the big two cornerstones, and we will of course not talk about function optimization here at all, but that's a big issue. I mean, the whole neural network, TensorFlow business, and so on. This is just function optimization from my perspective. Good.
Just a second, please. And then the second question is, do the loss function and the negative log likelihood share the same minimum?
So you mean the loss function? Well, the loss function is, of course, the question, what is the loss function, right?
So I usually use cross entropy or the H entropy.
Well, you can, this is with the loss function, if you're from this kind of machine learning perspective on loss functions, I would consider the log likelihood function as a specific loss function that you're trying to maximize. Of course, you can build different things into these kind of loss functions. For a typical beginner's thing is, of course, regularization, where you, in addition to having kind of a maximum likelihood term, you have some term that penalizes the values of your parameters so that they are small and so on. So in general, I would understand loss functions as either heuristic functions that you come up, for example, ordinary least squares is one of these typical heuristic loss functions where you say, okay, I want to minimize the squared deviation. Under a probabilistic setting, these then sometimes correspond to maximum likelihood. Then you can have these kind of more kind of these Lasso kind of things where you say, I want sparse, I encourage sparsity, so I put this in my loss function. So I would view log likelihood functions as special cases of this general idea of a loss function, but log likelihood functions as being derived as loss functions under a fairly established theoretical framework, namely probabilistic modeling. Other loss functions, like the things that you mentioned, they also can derive from some theoretical framework, or they derive more from some heuristics of what might be a good idea to minimize here. So that's the way I go. But then, of course, the aim is the same. You try to minimize the loss or maximize the likelihood. Yeah? So my favorite loss function is the variational free energy in this sense, if you want. But that's my personal taste. So, goodbye. Then see you at 1:15 in the other room for the Übung. Thank you.